Hello, everyone. Thanks for joining our talk today. This is a presentation on the Core 5 verification test bench from the OpenHW Group, where we're working on commercial quality verification of open source RISC-V cores. My name is Rick O'Connor, and I'm with the OpenHW Group. And in today's talk, I'll give you a brief overview of the OpenHW Group and describe the Core 5 verification test bench within our technical working group and the task groups that drive this project. And we'll also have Simon Davidmann, CEO at Imperas, talk about how the Imperas RISC-V golden reference model is used in the test bench. And then we'll bring in Aimee Sutton, an applications engineer from Metrics, to talk about how we use the Metrics Cloud-based EDA Platform for the verification test bench that we host in the cloud. So quickly on OpenHW Group, this is a nonprofit global organization driving open source implementations. And in particular, we're focused on high quality verification of these open source IP blocks so they can be used in high volume SoCs with major semiconductor companies. We have developers across the world in the Americas, in Europe, and in Asia, and very, very strong support across industry with more than 52 plus members and partners from industry, from a research ecosystem, as well as a partner ecosystem to help us bring these open source artifacts to the community. The way that we're structured within the OpenHW Group is through a series of various working groups and task groups. And today I'm just going to touch very briefly on the technical working group, which has a number of task groups. Two in particular that we'll focus on today are the cores task group and then specifically the verification task group where this open source Core 5 verification test bench is hosted. The technical working group is chaired by Sebastian Ahmed from Silicon Labs and Jerry Zing from NXP. And this is basically the R&D function, if you will, of the OpenHW Group, where we drive all of the technical projects that happen within the ecosystem. And one of the task groups inside the TWG is the cores task group, chaired by Ariane Bink from Silicon Labs and Jérôme Guévremont from Thales. And this is where we curate the family of Core 5 RISC-V cores. These are open source RISC-V cores that originated at the Pulp Platform group under Luca Benini's leadership at ETH Zurich. So in particular, the CVE4, the RISC-V core, is a 32-bit embedded class 4-stage core. And that's the focus of the verification task group right now and the Core 5 verification test bench that we'll talk about in a minute. And then also the Ariane, now that we call the CVA6. It's a 6-stage application class core, and that's available in 32-bit and 64-bit implementations. But for today, we're going to focus on our verification task group, which is chaired by Leo Wang from FutureWay Technologies and Steve Richmond from Silicon Labs. And the mandate of the verification task group, and this is, I think, a bit of an important distinction in terms of other open source activities that are underway in the ecosystem. What we're focused on is developing a best-in-class open source verification test bench that leverages commercial tool flows. So we're not trying to reinvent how large volume semiconductor companies verify their designs, the IP they use, and the SoCs that they develop. What we're trying to do is leverage standard System Verilog UVM-based flows and make sure that the IP that we're curating fits well within those flows and is verified in a methodology that these companies are used to using. So I'm going to walk you through the Core 5 verification test bench UVM environment. And the chart that you see now has a number of elements in it. On the left-hand side are the test cases and stimulus that drive the test bench. So we're using the Google random instruction generator to generate random instructions. And there's a number of manually written test programs as well that we drive into the test bench. All of this is invoked by GCC toolchain that is being worked on by our software task group and upstreamed into mainline GCC. And all initiated and run using the UVM run flow. Those test programs are then loaded into instruction memory as well, mapped into a virtual set of memory map peripherals. We can execute the DUT, in this case the E4, the Embedded Class 4-stage core. And the same test program runs concurrently on the Imperas golden reference model, a RISC-V reference model, which Simon will talk about in a minute. And we use assertions from our formal environment as well, driving into the core. And then use agents and UVM sequences so that we can execute various test sequences independent of the test program. And all of this is executed on a instruction by instruction basis with a step and compare functionality built into the test bench at the retire of every instruction, where we look at all the CSRs, GPRs, and PC at the end, at the retire of every instruction. This whole environment is run using in the cloud on the Metrics EDA platform, using a single UVM instruction to execute the whole environment, and we run regressions on a nightly basis. So it's a pretty cool environment. It is what most major semiconductor companies would build on their own if they were doing internal development or internal verification of some custom IP. And we're thrilled to have this project underway within the OpenHW Group. So with that, I'm going to switch over to Simon. We'll bring Simon in to talk about how the Imperas RISC-V golden reference model is used within the Core 5 verification test bench. Simon?
Great. So thanks very much, Rick. And it's very interesting here you explain how the UVM test bench and everything works. I'm going to explain a little bit about the Imperas technology and how it works inside that. There are already several bits to what we offer. The first is the simulator. RISC-V OVP Sim is our sort of generic simulator that we make available in the RISC-V world. And we make it freely available on GitHub as a reference. And it's actually used by many different people across the industry in there. And it's based around our core simulation technology. And our simulator is designed to work in a verification environment and in standard DV methodologies. And those vary from the sort of trace and compare methodologies where you trace and then post-compare. So you generate a trace with one reference and then with the device under test and compare it. And people use that where they have instruction stream generators like the Google RISC-V DV that Rick mentioned in the UVM test bench here. Another approach is the signature base, where during simulation, our simulators can dump out a signature, which can then be compared, again, like a trace, but it's a signature of the test. And that's how, for example, the RISC-V compliance suite works, or technologies that another generator, Valtrix, uses. And then there's the System Verilog encapsulation, which is actually, we think, probably the best way, where the model is encapsulated in your major simulations. And I'll be talking about that in a future slide here. And that's really used in the step and compare methodology, which is how our technology is used as a reference in the OpenHW test bench. So it's a key part, how the simulator is used in the methodology. And the reference models can be, our model is a full sort of envelope model, so it can be configured to anything that the user needs in terms of custom instructions as well in there, or custom CSRs. And they're very easy. We have flows for putting those in so that, again, you don't perturb the existing verified model as well. So you can extend things quite easily with our methodology. And we spend a lot of time understanding people's methodologies, including the DV, but also how the generators work and how people do things with functional coverage. And we actually can generate functional coverage Verilog source code from our technology. And then the last bit of our sort of support is we provide test suites, actually. We have a comprehensive set of test suites that we've developed. And most recently, we've just released our vector test suite, which is the first one of those, which is a very large test suite configured for specific customers' vector engines. And those are available from us. So that's also support for RISC-V. In terms of the model, as I said, it's a configurable envelope model, and it covers the whole RISC-V from 32, 64-bit, all of the different options in there, from the standard ratified stuff to the latest vector and bit manipulation standards in there. And we have those are all available, and we regularly update those because the standards are changing quite frequently at the moment, especially the vectors as it's becoming stable. And then we just put into beta test our hypervisor simulation, or the model of the hypervisor in there. And we've got work on the PAC DSP, PDSP, and also the crypto. And the specs are still in flux, so we haven't released those. And we have a whole library of models which cover the main sort of IP providers of RISC-V cores, from the commercial ones like Andes and Sci5 to the open source ones like OpenHW and Low Risk. So we have a library of all these models. And our reference model is used as in many different places. For example, in the compliance working group, it's a reference standard that generates the signatures there. It's used by the commercial vendors, some of the stream generator people as well, and obviously OpenHW, which we're going to talk a little bit more on. We actually have a lot of other customers who don't go public on the usage of it. And actually seeing a lot of our stuff comes from GitHub for free, we don't know a lot of the uses until they sort of ask us questions and report issues. So let's move on now to the model encapsulation and how it's used in the OpenHW test bench. So we basically take our RISC-V model as an object, and is written in C, and we wrap that here in a System Verilog test bench, you can see in the light blue. And we access the C model in Verilog through the standard System Verilog DPI APIs, so that you have C functions down in the model, which then get pushed up into the Verilog domain. So you end up with a System Verilog module that you can just instance with an interface of buses and control signals into your System Verilog test bench. And then you can completely control it just like you would do some RTL. But it also has some other APIs, so you can extract all the internal state, the GPRs, and the different registers that are inside it for comparison in your Verilog test bench. And so you take this System Verilog module, which wraps the OVP model, and you put that in a test bench side by side with your RISC-V core, your RTL. And this is what Rick showed earlier for the OpenHW one. And you basically load your programs into the memory, whether they're directed tests or random generated tests, and then you step them, and at every, as Rick mentioned, at every instruction retire, you can check not just the PC, but the whole state of the internal machine. And this is exceptionally good for doing large programs which have come from generators, but also the asynchronous stuff of debug mode, and also interrupts coming in, because they're typically very hard to verify, and having a step and compare methodology allows you to really do that. And so at every instruction, basically, you're comparing the state of things. So in conclusion here, Imperas, we've been working with the OpenHW Group for about a year, because one of the key things that I think differentiates the OpenHW Group from a lot of the other people is the focus on verification and using standard industry flows, but to use the verification, the standard industry flows, to build an open source RISC-V core. So it's going to be delivering the highest quality core that's available in there. And so I think as people look at different cores, they'll find the OpenHW one is verified far better than a lot of the others. And the key thing about it is that when you take and access the core as open source, you can get the UVM test bench and the whole verification approach that OpenHW has developed with its partners, Imperas and Metrics, etc. And then if you add your own custom instructions or CSRs, then you can use that test bench and extend it. So I believe a key value that the OpenHW Group delivers is this verification and the quality of the core. So thanks very much. Back to you, Rick.
Great. Thanks very much, Simon. Okay, now we'll throw it over to Aimee Sutton from Metrics to talk about how we use the Metrics Cloud-based EDA Platform in the Core 5 verification test bench. Aimee?
Thanks for the introduction, Rick. Hello, everyone. I'm here to tell you a bit about Metrics and about the role we play with the OpenHW Group. So Metrics is a cloud-based provider of EDA tools. We have all the tools you need to perform your design verification of custom silicon, and we offer them in a cloud-based platform. We have a System Verilog simulator that we provide using a pay-per-use business model. As well, we have custom software for dispatching jobs in the cloud that takes advantage of the scalability and availability of resources there. And we have a suite of verification management and debug tools that we offer in a web-based platform. So let me tell you a bit about Metrics' role with the OpenHW Group. We provide the tool suite that I described for use by OpenHW Group members, and we feel that the features of our product are a natural fit for the needs of the OpenHW Group, or really any team that is highly distributed and has dynamic simulation needs. So one example of this is continuous integration. That's the practice where your changes to code are automatically tested upon commit before they become part of the master branch of your code repository. So the OpenHW Group consists of members from many different organizations, and there's a bit of overhead to managing a distributed project like this. Metrics helps with that task by providing a single simulator that can be used as a reference by all members, even when they work at different companies, and helping with the approval of pull requests by automatically launching simulations when someone submits a pull request. And if those simulations are not successful, the results are available for the author of the pull request to view and debug using their web browser. Collaborative development. This is closely related to what I just described. Our debug tools with Metrics are available from any web browser, anywhere. You don't need to install any tools to work with Metrics. All you need is a Git repository. Results and artifacts are easy to share. So that means that you and your colleague can be looking at the same results on your web browser in two very different locations. And with the OpenHW Group and members working in different organizations, they may have barriers to sharing these things using their company's proprietary tools, but those barriers don't exist with Metrics. And in the near future, we'll be providing a public view of regression and coverage results so that the public will be able to see the same view of the progress of the OpenHW Group's DV efforts, the same view that the members can currently see. Another asset that we provide to OpenHW is simulation capacity. So when you become a Metrics customer, you don't need to install any software, as I said. You don't need to own your own compute farm. We provide all the resources that you need to run coverage closure regressions, continuous integration regressions, using the resources in the cloud. And we provide unlimited licenses of our System Verilog simulator, where you just pay for the amount of time that the simulator is actually running. And there's no assembly required. We take care of all of this for you, dispatching jobs, publishing results, storing artifacts, so you can just focus on the DV work. With an organization like OpenHW, they don't have a compute farm like a traditional company. So Metrics has provided the ability for them to do DV as any commercial organization would do. Instead, they're using the cloud instead of a local compute farm. Coverage closure. This is another key metric that's used to assure quality of custom silicon. Achieving coverage closure is a process that typically takes a lot of simulation runs, a lot of compute power, and this is something that's also a perfect fit for Metrics and our cloud-based tools because we can scale to meet the demands. So if you're running 1,000 simulations, we will run them all in parallel. And you can dynamically add more resources as required. Coverage is always available in our web application. So it's not an afterthought with Metrics. It's something that you always see with every regression you run. Coverage merging is automatic. So that's a task that tends to be CPU and time intensive, and it's something we also offload from our users whenever your design or test bench contains System Verilog assertions or System Verilog cover groups. will automatically merge the results and make those available to you via our web application. The other feature we provide is test ranking, and that's something that helps you guide your stimulus as you work towards coverage closure. You can see which tests are getting you the highest incremental contribution to coverage and helping you to focus on those and then address the holes. The other feature of Metrics that helps open hardware is remote support. So because we're cloud native, we can provide support to any user no matter where they're located. We can see the same view that those users are seeing, and it's easier for us to debug problems. And at Metrics, we are big fans of open source development and are very happy to support the ongoing work of the OpenHW Group. So I'm just going to give you a quick overview in this slide of how OpenHW Group members interact with Metrics. So the icon in the top left-hand corner represents the members of the OpenHW Group and shows that they have two interfaces to Metrics. The one at the bottom is through GitHub, through their Git repository. At Metrics, Git is our mechanism for getting users' data into the cloud. The arrow at the right shows an interface to our web platform, where we have our results, debug tools, coverage browser, and that's available in any web browser. So the workflow that OpenHW is using with Metrics is that OpenHW Group members will commit code to their Git repository, and that commit can launch either continuous integration regression, or they can be working towards coverage closure, so a larger regression. In both cases, we'll launch all simulations in parallel, each on a separate virtual machine running in the cloud. And as the results complete, they'll be published to our database. We take care of storing all artifacts associated with simulations, so log files, waveforms, coverage databases. So there's no need to worry about storage. And our database is used to populate our web application, where you can review results, you can view log files, debug using our waveform viewer, and view coverage results. And that information is the feedback that goes back to the team members to refine their test cases or their stimulus, make changes in GitHub, do a Git push, and continue the cycle of testing and working towards coverage closure. And with that, I'm going to send it back to Rick. Thank you for your attention.
Great. Thanks very much, Aimee. And thanks everyone for attending. We're now ready to open up for a Q&A session. Thanks very much.